Hello class, in this video we'll be talking about Lewis structures or Lewis dot structures. I'm going to start off the video by reviewing some things about different atoms, for example how we know they're stable and how atoms gain or lose electrons in order to become stable. We will also be drawing some Bohr models, so if you haven't seen my video on Bohr models or you don't know how to draw Bohr models, it would be helpful to see that video first. Then we'll get into drawing some Lewis dot structures for ionic as well as covalent substances. So without further ado, here we go. First, let's recall some terminology. The term valence electrons is going to refer to the electrons that are in your outermost energy level. Now with Bohr's model, we have our nucleus in the center and then the surrounding rings. Those rings or those orbits are called your energy levels. We also know that our number of valence electrons matches the group number. So if I'm in group 3, then I have 3 valence electrons. If I'm in group 7, then I have 7 valence electrons. Your groups, keep that in mind, are your vertical columns. Not the horizontal rows, but the vertical. So, for example, chlorine, let's look at the sodium atom first. On the periodic table, we have that sodium has an atomic number of 11, so it has 11 protons. Because we're looking at atoms, it's also going to have 11 electrons. So if I was to draw the Bohr model for this, my protons and my neutrons would be in the nucleus. The first energy level can hold up to 2, so I'm going to put 2 electrons in my first energy level. The second energy level can hold up to 8. I'm trying to place 11 electrons. So right now I have 8, 9, 10. I will need another energy level in order to place my 11th electron. For chlorine, 17 protons, 17 electrons. Again, I'm getting that from the atomic number on the periodic table. And these are atoms. So we know that there's going to be the same number of protons as neutrons. So 17 electrons that I'm trying to place. Again, that first energy level can only hold 2. The second energy level can only hold 8. Right now I've got 10 electrons, so I need a third energy level to hold my other 7 electrons. So those are the Bohr models for sodium and chlorine. Now, in order to be stable, your atoms are stable when they have a completely full energy level, your outer energy level. So in this case, this one's our outer one right now. I only have 1 electron in it. It could hold up to 8. So this is not filled. This one here only has 7. This could also hold up to 8. It's not a filled energy level. So technically these two atoms are not stable because they don't have a full outer energy level. But if sodium were to lose this electron and didn't have that electron, we'd completely knock out that outer energy level, then we'd have 8. It would be filled. If chlorine were to gain an electron, so instead of 7, if this gained 1 more, then it would be at 8 and it'd be a completely filled orbital. So that's why ions occur. Sodium would want to lose that electron, and if it lost that electron, then we'd become Na+. So that's where the Na+ comes from. And if we look on the back of our periodic table that you got in class, sodium has a +1 charge. If chlorine was to gain another electron in order to be stable, it would become Cl, gain another electron, Cl-. So that's why they become ions, in order to fill those outer energy levels. Now, for Lewis dot diagrams, keep in mind that your valence electrons are the same number of your group numbers. And what I could do with these diagrams is I could show that this electron could transfer over here in order to become Na+ and Cl-. But in order to get to this electron, I had to draw a whole bunch of circles. I had to draw a whole bunch of my energy levels. I had to count my electrons, count my protons. The Bohr model does take some time. Scientists are pretty lazy though, so they came up with a way to shorten and abbreviate your Bohr model so that you don't have to draw all your energy levels just to notice, oh, this electron could go over here. Instead, they draw something called Lewis dot diagrams. So we're still accounting for our valence electrons, which are the electrons in that last ring, but those are the only electrons we care about. We don't care about these other electrons that have those full shells. So I'm going to give a few Lewis dot diagrams. These are the elements in period 2, so the lithium, beryllium, I'm going to be moving across our second period. Lithium is in group 1, so it has just one valence electron. So I'm going to draw one dot to represent my electron, and I'm going to put that around the symbol for lithium. Beryllium is in group 2, so it has two valence electrons. I'm going to put 2 dots. Now, because our electrons repel, they're not going to be on the same side of my symbol. Notice I put 1 dot here and 1 dot here. Boron, group 3. We've got 3 valence electrons. So I'm going to put 3 dots around my boron. Again, they repel, so try to spread them out as much as possible. Chlorine, group 4. So I've got 4 electrons around, carbon. Carbon is group 4. Nitrogen is group 5. Okay, so 1, 2, 3, 4. If we think of this as a box, there's only 4 sides. So I'm going to pair up my 5th electron so that these 2 are on the same side, and then I've got 3 that are on either side. So if you think of a box, I've got 2 on this side, and then 1 around here, 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 and here. So that's kind of how I'm circling my dots. Oxygen, 1 on the left, 1 on the top, 1 on the right, 1 on the bottom. There's 4, 5, 6. So that would be the Lewis dot diagram of oxygen. Fluorine is in group 7, so 1, 2, 3, 4, 5, 6, 7. And then neon is in group 8, so it would have 8 valence electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. Some things to note, we are using the 4 sides. Don't make them equally spaced around there. We do want it to look kind of like a box so that there's 2 on either side. Also, these show up as pairs. Sometimes I ask how many unpaired, unshared pairs are there, or how many pairs do we have of electrons. So you can count them as pairs or you can count them as individuals. Other final detail, it does not matter where your individual dot shows up. So for example, for fluorine, I could have just as easily drawn it like this, where I have my individual lone dot on the right side, or it could have been on the top, or it could have been on the left. It does not have to be on the bottom. As long as there are 7 dots around fluorine, 7 valence electrons around fluorine, your Lewis dot diagram is fine. Okay, so if we are looking at ionic bonds, this was when we have one electron taken from one atom and given to a different atom. So these are a transfer of electrons. That's the technical term that I use, transferred of electrons. This happens between metals and nonmetals. For example, our sodium being a metal and our chlorine being a nonmetal. We saw earlier in our Bohr model, so for sodium, we had 1 valence electron out in sodium, so I'm going to draw Na with my 1 valence electron. Chlorine, we had 7, so I'm going to draw chlorine with 7 valence electrons around it. I want sodium to have a complete shell. It wants to get rid of this extra electron. Chlorine wants to have a complete shell. It wants to gain another electron. So this electron transfers to my chlorine. And if I was to write this in as an equation, my sodium loses its electron. So I can write it like that. It does have a charge on it because it lost its electron. And then I can write my chlorine with its dots, all 8 now, because it gained the one from sodium. In chemistry, we put brackets around our Lewis structures, and then we can put that it has a negative charge, just to make sure that our electrons are kind of in a bracket or a box so we don't lose track of those. Let's try another example. Let's try Na and oxygen. So sodium, again, has that one valence electron. Oxygen is in group 6, so it has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. Sodium can give 1 electron here, and that makes sodium a happy camper. But oxygen's not a happy camper yet. We don't have 8 electrons around oxygen. So in a compound between sodium and oxygen, it would require another sodium in order to donate all of the electrons to go to oxygen. So this electron could come and pair up with this one, and then I would have 1, 2, 3, 4, 5, 6, 7, 8 electrons. I would need 2 of those sodium ions. So I would write it as Na2, because I have 2 of my sodiums. My oxygen now has an octet around it. It has a charge of 2 minus. If I was to simplify this and drop out the Lewis dots, just write the compounds, the compound formula, it'd be Na2O. And that's what we saw earlier in order to balance those charges. The 2 negative, I need 2 of my sodiums to balance that 2 negative. So that is kind of the background of why there's 2 sodiums for 1 oxygen. We're trying to get those 2 electrons in order to fulfill oxygen's outer shell. Now, into some covalent bonds. These are more of what you'll be dealing with, not so much the ionic. When your electrons of one atom are shared with another atom. So this happens between nonmetals and nonmetals. It's not this get rid of and completely steal type of transfer. It's instead, hey, you need this electron and I need this electron, so let's share it. Between your nonmetals and nonmetals, again, this is all on the right side of your periodic table. So for example, let's look at CH3, methane. Excuse me, CH4. And let me go ahead and draw it on here. CH4, methane. If we were to draw the Lewis structure for this, I would write carbon. There are 4 valence electrons around carbon because it is in group 4. This 4 refers to how many hydrogens I have. I have 1, 2, 3, 4 hydrogens because that's what I'm given in my formula. And if I look for hydrogen, hydrogen is in group 1, so I have 1 valence electron for each of those hydrogens. Now, hydrogen wants another electron. It can have a maximum of 2. It wants to gain another electron. Carbon also wants to gain more electrons. It wants to have a complete outer energy level of 8. So, if hydrogen shares this electron with carbon, and carbon shares this electron with hydrogen, then for some of the time, hydrogen can have 2 electrons. And carbon, if it does that with all of these hydrogens, it could share, well, it has 1, 2, 3, 4 of its own, and then it could borrow 1, 2, 3, 4 from the hydrogens. So carbon would have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons because they're sharing. Now, in order to draw the Lewis structure for this, let me draw it like this. When you have a pair of electrons, we draw it as a line. So that 1 electron lives over here, 1 electron lives over here, but they can move back and forth along that line. So in this case, I have a line between 4 hydrogens. So this would be the Lewis structure for CH4, or methane. The lines representing a pair of electrons. Let's try another example, HF. So again, hydrogen, group 1, has just 1 valence electron. Fluorine, Group 7 has 1, 2, 3, 4, 5, 6, 7 valence electrons. Fluorine wants one more electron, hydrogen wants one more electron. If they share those two right there, then fluorine could have 8 sometimes and hydrogen could have 2 sometimes. So I'm going to draw that as H, F, and then I will put in those shared electrons. Now, what happened to these electrons? Well, they're still there. So I do still need to include those unshared electrons on fluorine. These ones are going to stay with fluorine. They aren't going to bounce back to hydrogen. It's just this set right here that's being shared between our two elements. Okay? A few other examples. NF3. From here on out, I'm just going to keep doing some examples. I am working through some of the ones on your page 14. I'm working through some beginning and middle levels. So for the rest of my video, I'm just going to do a whole bunch of examples. NF3, nitrogen, is in group 5. So it means it has 5 valence electrons around it. 1, 2, 3, 4, 5. I have 3 fluorines. So 1, 2, 3. Fluorine is in group 7. So each of those fluorines have 7 electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How can I share electrons so that each of them have 8? Well, this fluorine needs just 1 electron from nitrogen, so let's share that electron with nitrogen. This fluorine needs 1 electron, so let's share it that way. This fluorine needs 1 electron, let's share it that way. So 1, 2, 3, 4, 5, 6, 7, 8. Now all of my fluorines have 8. Let's see if my nitrogen has 8. 1, 2, 3, 4, 5, 6, 7, 8. My nitrogen also has 8. So if I wanted to rewrite this, I could put the N. I have bonds to my fluorine. Those are my shared electrons. I also have to include all of my unshared electrons. So I've got those 2, and then I've got the ones around each of my fluorine. That would be the Lewis structure for NF3. Now, those are pretty basic examples. We're looking at just one line between each of these elements in order to share one pair of electrons. There are some examples that you need to share more than just one set. One example would be O2. Oxygen is in group 6. Each oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen needs 2 more electrons. This oxygen needs 2 more electrons. So if I share those, that would give oxygen 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, they need to share 1 more electron. So we're going to share these 2 as well. And if I look at one oxygen, that would now have 1, 2, 3, 4, 5, 6, 7, 8 associated with this oxygen. And because this is a mirror image, we also have 8 for this oxygen. So I'm sharing 2 sets of electrons. I'm going to draw that like this. Not one line, but I now need a double bond. So it looks kind of like an equal sign. It's showing that there's now 4 electrons being shared between those oxygens. And I do have to include those other non-shared pairs, the ones that are individual for each of those oxygens. So that is what oxygen looks like. That's the substance that we breathe in. Let's do a few more challenging examples. CO2, so I've got 1 carbon and 2 oxygens. Carbon is in groups 4, so I've got 4 dots around it. Oxygen is in group 6, so I've got 6 dots around it. And I've got this oxygen in group 6. Again, it doesn't matter how your dots are arranged. We're just trying to count them up so that they can share. All right, carbon. I have 1, 2, 3, 4. I need 4 electrons. So let me share that one with oxygen and that one with oxygen. Ooh, but that only gets me 1, 2, 3, 4, 5, 6 electrons around my carbon. I need to share 2 more electrons in order to fulfill the octet of carbon. Let's count my oxygen. I've got 1, 2, 3, 4, 5, 6, 7 electrons around this oxygen. I also have 1, 2, 3, 4, 5, 6, 7 electrons around this oxygen. Oxygen will also need 1 more electron. So, what if I was to share this electron with this one, that carbon? That would give this oxygen 1, 2, 3, 4, 5, 6, 7, 8. 8 of those that are being shared. Let me try the same thing over here with my carbon and that oxygen. 1, 2, 3, 4, 5, 6, 7, 8. That gives 8 electrons around oxygen. Now let's see all the electrons around carbon. It has these 4, but also this one, that one, this one, and this one. So these 4 are being shared by the oxygen. So now all of these elements have 8 electrons around them. We have fulfilled that octet. If I was to draw my Lewis structure, I'm sharing 2 sets. So I'm going to put a double bond to oxygen, include my lone pairs, and then I have a double bond to this oxygen, and I'm going to include those unshared or lone pairs. Okay? And now they all have 8. One more example, just because it has a few more atoms in it. H, C, and N. Hydrogen is in group 1, has 1 dot around it. Carbon is in group 4, so it's going to have 4 valence electrons around it. Nitrogen is in group 5. It has 5 valence electrons around it. I know I'm going to share at least those ones. Hydrogen's happy, it now has 2. Carbon has 1, 2, 3, 4, 5, 6. I need 2 more electrons for my carbon. Nitrogen is 1, 2, 3, 4, 5, 6. So I need 2 more electrons for nitrogen. If I share those electrons, and if I share those electrons, then carbon would have 1, 2, 3, 4, 5, 6, 7, 8. So those are the 8 electrons around carbon. Nitrogen would have 1, 2, 3, 4, 5, 6, 7, 8. So with that diagram, we now have 8 across each of our elements. So to rewrite this, hydrogen, I just have 1 single line between hydrogen and carbon, but now I have 3 lines connecting my carbon and my nitrogen. I call that a triple bond. So there's my triple bond representing 2, 4, 6 electrons that are being shared between carbon and nitrogen, and then I still need my lone pair or my unshared pair on my nitrogen. Okay? Alrighty, kind of a long video, but I hope that was helpful for drawing Lewis structures. Thanks, and have a great day. Bye!